All right, so get ready because we're about to do a deep dive into the world of early electromagnetic instruments.
Oh, this is going to be fascinating.
I know, right? You sent over some really interesting excerpts from,
From the Project Gutenberg ebook of the earliest electromagnetic instruments.
yeah, that's the one.
It's a great read.
It is. And I think we're going to uncover some really cool stuff about how scientists went from just observing electricity to actually like creating tools and, you know,
To measure it.
yeah, to measure it, to understand it.
Absolutely. And we're focusing on this really pivotal time period between 1800 and 1820,
Okay.
right after Alessandro Volta uh, announced his invention of the voltaic pile,
Oh,
which
yeah, the first electric battery.
exactly, the first electric battery. It was a time of just immense excitement, so many new discoveries.
I bet.
But the scientists were really struggling because they didn't have reliable tool to measure and compare all these electrical effects they were seeing.
So it's like they had this powerful new engine,
Yeah.
but they didn't have like any gauges or,
The speedometer.
yeah, a speedometer to figure out how fast it could go, how much fuel it was using.
That is a perfect analogy. And that's where this whole story of the first electromagnetic instruments, or multipliers as they call them, comes in.
Multipliers. Okay.
And what's amazing is that three different individuals all came up with this idea almost simultaneously.
Oh, wow.
Johann Schweiger, Johann Poggendorf, and James Cumming.
Three different people in different places all at the same time.
Pretty much.
Ye-
And there was, of course, a bit of controversy about who should get the credit.
Oh, I bet.
We'll dive into all that.
Yeah, definitely. We've got to unpack that.
Absolutely.
But first, can you kind of set the stage for us a little bit? What was it like to actually study electricity way back then?
Well, imagine trying to study something as elusive as electricity, right? Without accurate measuring tools.
That's going to be tough.
Yeah, it was. Early experiments really just relied on basic observations.
Like what?
Things like how bright a spark was,
Oh, wait.
or how intense an electric shock felt.
Wait, are you serious? They were using their bodies to like...
Kind of. Volta himself actually described testing his pile, putting it on his tongue, his ears, even his eyes. He was really fascinated by how electricity affected the body.
I guess you could say he was really charged up about his invention.
Uh-huh. Very good. But in all seriousness, Volta's pile was groundbreaking.
Yeah.
But he didn't really take that next step.
Of making tools to measure it.
Exactly. That's what I meant by a missed opportunity earlier.
Gotcha.
And here's where it gets even crazier. For 20 years after the voltaic pile was invented,
20 years.
scientists were using it right alongside compasses.
Compasses? I don't get it. What do compasses have to do with electricity?
Well, think about it. Compasses rely on magnetism, right?
Okay.
And as it turns out, electric currents actually create magnetic fields.
Okay.
But nobody made that connection for 2 decades. It wasn't until 1820 that Hans Christian Ørsted finally had that aha moment and realized the link.
So they were working with these two fundamental forces side by side and just never realized they were connected.
It's wild, isn't it?
Yeah. So once Ørsted made this discovery, what happened? Was it like a starting pistol for everyone to try and build an instrument that could measure these effects?
Oh, absolutely. It was a game changer. And that's where our three protagonists come in: Schweiger, Poggendorf, and Cumming.
Yeah, you mentioned them earlier, the multiplier guys.
That's them. They all independently hit on this idea for a device based on Ørsted's findings.
Okay, but hold on. What exactly is a multiplier and how does it work?
Well, remember how Ørsted discovered that an electric current creates a magnetic field?
Yeah.
So the idea is if you coil a wire and run a current through it, the magnetic field around the wire actually gets stronger.
Yep.
And if you place a compass needle near this coil,
Yeah.
the needle will move. And how much it moves tells you how strong the current is.
So it's like a megaphone for magnetism. The coil amplifies the magnetic field, making it strong enough to move the needle.
That is a perfect way to put it.
If.
And the multiplier was a huge leap forward because it let scientists detect even really weak currents, which meant more precise measurements.
Okay, so let's start with Schweiger. What was his approach to this whole multiplier thing?
Schweiger, he was obsessed with building an instrument that could detect even the tiniest electrical signals.
Really?
Oh yeah, he compared the sensitivity of his early devices to like a twitching nerve.
Wow. So it seems like he was more into just detecting these subtle currents rather than actually measuring how strong they were.
Yeah, I think that's right. His early multipliers were very simple, just coils of wire, basically.
Okay.
But he experimented with all sorts of shapes, like bow-shaped coils or coils around glass tubes,
Interesting.
always trying to make it more sensitive.
Driven by pure scientific curiosity, huh?
Absolutely. But it's important to note that his early attempts to find magnetic effects from Electrostatic machines, those were unsuccessful.
So even with this new tool, there were still
Oh,
obstacles.
for sure. It was a lot of trial and error.
It makes you wonder, did Poggendorf have that same drive for sensitivity, or was he after something different?
Poggendorf, he was a different kind of thinker, much more analytical.
Mhm.
He was interested in really understanding the relationship between electricity and magnetism, not just detecting it.
Hmm.
He called his device a magnetic condenser. And unlike Schweiger, he took a very systematic approach.
Systematic.
He would meticulously experiment with everything, the number of turns in the coil, the thickness of the wire, even the arrangement of the battery cells,
Wow.
all to figure out how to maximize the effect on the compass needle.
So he was really trying to crack the code of how electricity and magnetism work together.
Exactly. And one of his key findings was that the amplifying power of the coil, it had a limit.
What do you mean?
Adding more and more turns to the coil didn't make the magnetic field infinitely stronger. There was a sweet spot.
Interesting.
And that hinted at this complex interplay between the two forces.
That's fascinating. So he was sort of mapping out the hidden rules of these invisible forces.
Yeah, that's a great way to put it. And you know what else he discovered?
What's that?
Materials that conducted electricity, but not as well as a normal conductor. He called them semiconductors.
Wait a minute.
What is it?
Are we talking about the same semiconductors that are like the heart of computers and smartphones?
The very same. It's incredible, right? His experiments with tiny currents and coils of wire inadvertently laid the groundwork for the digital age.
That's mind-blowing. So we've got Schweiger's quest for sensitivity, Poggendorf's meticulous analysis, and then there's Cumming.
Right, Cumming.
What made his approach unique?
Cumming was all about practicality.
Okay.
While his galvanoscope was based on the same idea as the others, he took it a step further.
How so?
He actually calibrated it to measure the strength of the electric current.
Ah, so he turned it into a real measuring tool.
Exactly. He wanted to quantify how strong the current was, not just detect it.
So how did he do that?
Well, he used a separate straight wire galvanometer that he could calibrate.
Okay, I'm not sure I follow.
Imagine a straight wire with a sliding contact. The distance between the contact and the compass needle is related to the current strength.
Oh, I see. So by moving the contact and watching the needle, he could figure out how much current was flowing.
Exactly. He created a ruler for electricity. And with his new ability to measure, he confirmed the findings of Biot and Savart.
Who are they?
They had discovered that the needle's deflection was inversely proportional to the distance from the wire.
I'm not sure I understand all that, but it sounds important.
It was. It was a crucial step towards being able to mathematically describe electromagnetism.
Wow. So he was not only building instruments, but also using them to refine our understanding of these forces?
Absolutely. And he didn't stop there.
What else did he do?
He used his instruments to study something called galvanic effects of different materials.
What does that mean?
He would connect various substances to his voltaic pile and use his multiplier to figure out their, how should I put it, their electrical personality.
Electrical personality.
Basically, he wanted to know which materials were more likely to give up their electrons and which were more likely to attract them.
Ah, so he was figuring out how electricity flowed in different materials.
Exactly. This was crucial for understanding how batteries worked and would eventually lead to big advances in the field.
Okay, we've talked about how Cumming measured currents and studied different materials, but I think you also mentioned something about thermoelectricity.
You're right, I did. Cumming was fascinated by the connection between heat and electricity.
Wait, hold on. You're telling me heat can create electricity?
It can. If you join two different metals and heat one of the junctions, it generates a tiny electric current.
That's wild. So how did the multiplier help them study this?
Well, these thermoelectric currents are super weak,
I bet.
but the multiplier was sensitive enough to pick them up.
Wow.
So Cumming could experiment with different metals and temperatures and really start to understand what was going on.
So even though it started with something as simple as a compass and a coil of wire, this multiplier really opened up a whole world of electrical exploration.
It did. From measuring currents to figuring out the electrical personalities of materials to this whole connection between heat and electricity.
Amazing. It's incredible how far they came with such a basic tool.
It is. But remember, even with this powerful new tool, they were still facing a lot of challenges.
Like what?
Well, imagine working with crude batteries, coils they had to wind by hand, compass needles that weren't always perfectly balanced.
I bet that was frustrating.
It was. Plus, They were grappling with some fundamental questions about what electricity even was.
I'm all ears. What kind of debates were they having? So even with this new tool, they were facing challenges. What kind of questions were they struggling with?
Well, back then, they didn't really know what electricity was.
Really?
Some scientists thought it was like a fluid, others thought it was more like a force or even a vibration.
Wow, that's crazy. It's like trying to study a river, but you don't even know if it's made of water or molten lava or liquid nitrogen.
Uh-huh. That's a great way to put it. It really makes those challenges with the instruments seem almost easy in comparison.
For sure. So it sounds like they needed better instruments, A&D, better theories to really make any progress.
Exactly. Had to go hand in hand.
Got it.
But getting back to those practical challenges for a second, let's go back to Cummings' work with thermoelectricity for a minute.
Okay.
You're asking about how he used the multiplier to study that, right?
Yeah, the whole idea that heat can create electricity is still kind of blowing my mind.
Yeah, it's pretty wild. So remember how we were saying those thermoelectric currents are super weak?
Yeah.
Well, Cumming actually found a way to make his multiplier even more sensitive.
Really? How?
He would partially neutralize the Earth's magnetic field right where the compass needle was.
Now, wait a minute. Wouldn't that make the needle less responsive?
That's what's so clever about it. By carefully balancing out the Earth's magnetic influence with another magnet, he actually made the compass needle more susceptible to the tiny forces generated by the thermoelectric current.
Ah, so it's like tuning out the background noise so you can hear a faint whisper?
Exactly. And this technique, which they call the astatic principle, became a cornerstone of future galvanometer designs.
Wow. So he was basically fine-tuning the instrument to make it hyper-aware of those tiny currents. That's some serious scientific finesse.
It really is. So you see, Cummings' work wasn't just about making discoveries, but about refining the very tools of discovery.
That's really cool. You know, when you were describing how he calibrated his galvanometer using that straight wire and the sliding contact,
Right.
it made me wonder, did they even have standardized units for measuring electricity back then?
Ah, that's a great question. And it highlights another huge challenge they faced.
Yes,
They
right.
didn't have standardized units like we do now, amps and volts and all that.
So how did they compare their results? How did they know what a strong current was versus a weak one?
It was all relative. They might say that one current was twice as strong as another, or compare it to the deflection caused by a certain number of battery cells.
So it was more like comparing shades of blue than having a precise measurement.
Exactly. And that lack of standardization made it really hard to share and compare results between different researchers.
I bet. It's like everyone was speaking a slightly different dialect of the same language.
That's a good analogy. It's amazing how much progress they made. Despite all that, they were basically inventing the language and the tools of electromagnetism at the same time.
That's wild. But even with all these challenges, it seems like the multiplier really opened the floodgates for new discoveries.
It did. And as they refined those early instruments, they were able to dig deeper and deeper into these mysteries.
I'm curious, what were some of the other things they used the multiplier for, beyond just measuring current?
Well, one that really stands out is its use in studying the relationship between electricity and nerves.
Wait, they were using the multiplier to study nerves?
Yeah. Remember how Schweiger compared the sensitivity of his multiplier to a twitching nerve?
Mm-hmm.
Well, some scientists took that comparison pretty literally.
What do you mean?
They were beginning to understand that nerves transmitted signals through electrical impulses.
Okay.
So they started using the multiplier to try and detect and measure those bioelectric currents.
So they're using the same instrument, this coil of wire and a compass needle, to study both the fundamental forces of the universe and the workings of the human body.
It is pretty remarkable, and those findings had huge implications for how we understand the nervous system. They proved that nerve impulses weren't just some mystical thing, but an actual electrical phenomenon.
That must have been a huge breakthrough. It's like they were bridging the gap between physics and biology, showing that the same laws that govern electricity in a wire also govern the signals in our brains.
Absolutely. It was a major step forward.
So this simple device, the multiplier, it really sparked a revolution in so many fields, from measuring currents to mapping out the electrical behavior of materials to even understanding the human body.
It did. It's incredible how something so simple could have such a profound impact.
It makes me wonder, did they even foresee all of that when they were first tinkering with these coils and needles?
I doubt it. They were pioneers, driven by curiosity, and I'm sure they couldn't have imagined the full extent of their impact.
That's so inspiring. But it's also important to remember that their journey was full of setbacks, right?
Oh, absolutely. Scientific progress is rarely a straight line.
Makes their achievements all the more impressive. They were pushing the boundaries of knowledge with one hand tied behind their backs.
That's a great way to put it. And, that spirit of perseverance is something we can all learn from.
Speaking of challenges, you mentioned limitations in materials and technology, but were there other obstacles they had to overcome?
One of the biggest, and it's something we still face today, was simply getting people to understand and appreciate the importance of their work.
What do you mean?
Imagine trying to explain the significance of a multiplier or the concept of thermoelectricity to someone who had never even seen a battery before.
Uh-huh. Yeah, I can imagine that was a tough sell, like trying to explain the internet to someone who's never used a computer.
Exactly. These pioneers weren't just scientists, they were also educators, trying to convince the world that their discoveries were important.
And from what we've talked about today, it seems they were right. Their work really did lay the groundwork for so much of the technology we rely on today.
It did. But were there times when they faced pushback, you ask?
Yeah, was there any skepticism from other scientists or the public?
Oh, there definitely was.
Like what?
For example, when some researchers started using the multiplier to study nerves, there was quite a bit of resistance.
Really? Why?
Some people felt it was too reductionist, that it was oversimplifying the complexities of life by trying to explain it in purely electrical terms.
So they were basically being criticized for being too innovative.
You could say that. It just goes to show that new ideas, even if they're supported by evidence, often face an uphill battle.
That's so true. It takes a lot of courage to challenge the status quo and advocate for new ways of thinking.
It does. And that's another important lesson we can learn from these early pioneers. They weren't just brilliant scientists, but also trailblazers, paving the way for a more scientific and technologically advanced world.
Absolutely. Their stories remind us that science isn't just about cold, hard facts.
Right.
It's a human endeavor driven by passion and a desire to understand the world around us.
I completely agree. And speaking of human endeavors, didn't you mention earlier that there was a bit of controversy surrounding the development of the multiplier?
Oh, yeah, I did. It's easy to get caught up in the excitement of the discoveries, but we can't forget that science is also a human story, full of ambition and competition.
That's right.
So spill the tea. What kind of controversy are we talking about?
Well, remember how all three of them, Schweiger, Poggendorf, and Cumming, all came up with the idea for the multiplier independently?
Yeah, the scientific version of great minds think alike.
Exactly. But you can imagine when multiple people claim credit for the same discovery, things can get a little messy.
Oh, I bet. So who actually ended up getting the credit?
Well, to be fair, it really was a case of simultaneous discovery.
Okay.
They were all working on similar problems in different parts of the world, so it's not surprising they came up with similar solutions.
That makes sense.
But, of course, they all wanted to be recognized for their contribution.
No I in team, but there is an I in credit, right?
Mm.
So how did it all play out?
It wasn't always pretty. There were definitely some hurt feelings and accusations thrown around.
Oh, no.
Schweiger, in particular, felt that he didn't get enough recognition, especially compared to Poggendorf.
So even brilliant scientists aren't immune to a little jealousy.
Uh-huh. I guess not.
Yeah.
But in the end, history tends to even things out. Today, all three of them are recognized for their contributions to the development of the multiplier.
So a happy ending after all.
You could say that. And, it's a good reminder that science is ultimately a collaborative endeavor.
True.
Progress depends on many individuals building on each other's ideas, even if there are some bumps along the way.
I like that, science as a team sport.
Exactly.
And speaking of building on ideas, it's clear that the multiplier itself inspired so many new instruments and techniques. But did those early discoveries have a wider impact? Like, can we draw a line from those coils and compass needles to the technology we use every day?
Absolutely. The development of the multiplier was a crucial stepping stone. It paved the way for so many innovations.
So tell me, how did it shape the technological landscape? What kind of everyday devices wouldn't exist without their work?
Well, for starters, the multiplier was the precursor to the galvanometer, which became absolutely essential in electrical engineering.
So like the galvanometers used to design power grids and radios and stuff.
Exactly. And it goes even further. The multiplier also played a role in the development of the telegraph.
Really? The telegraph? How so?
Remember how sensitive the multiplier was to weak currents?
Yeah.
That sensitivity was crucial for detecting the faint signals that traveled over long telegraph wires.
So the same instrument used to study a frog's leg was also used to send messages across continents. That's mind-blowing.
It really is. And it doesn't stop there. Those early explorations into electromagnetism, sparked by the multiplier, eventually led to the development of the electric motor and the generator.
The backbone of modern society. So from a twitching compass needle to the roar of an electric motor, it's all connected.
It really is. It's amazing to think about, isn't it?
It is, and it really highlights the power of human curiosity, how a simple observation can lead to world-changing technologies.
Absolutely.
It makes me wonder, what are the multipliers of today? What simple tools or ideas are going to lead to the next technological revolution?
That's a great question. And it's one that I think we'll be grappling with for years to come.
I'm sure we will.
But one thing's for sure. The spirit of curiosity and innovation that drove those early pioneers is still alive and well today.
And that's what makes studying history so fascinating. It's not just about looking back, but about understanding how the past shapes the present and inspires the future.
I couldn't agree more. And as we delve deeper into these stories, we uncover these amazing connections, these threads of ingenuity that connect us all.
Well, this deep dive has been truly eye-opening. I have a whole new appreciation for those early pioneers of electromagnetism.
Me too.
But before we wrap up, I have one last question. What happened to those original multipliers? Do any of them still exist?
That's a great question. It takes us into the world of scientific preservation and the stories that objects can tell.
So what happened to those original multipliers? Do any of them still exist?
Well, some of them have been lost to time, which is, sadly pretty common for these early scientific instruments.
Yeah, I bet.
But thankfully, some have survived.
Really?
Yeah, and they're now in museums and private collections all over the world.
It's like finding a time capsule. I bet those instruments could tell some amazing stories.
They really can. That's why preserving these artifacts is so important. They give us a tangible connection to the past.
I can only imagine. To see firsthand the ingenuity of those early scientists.
Exactly. Do you want to hear about a really special one?
Absolutely, lay it on me.
There's a multiplier that was built by Schweiger himself.
No way.
It's in a museum in Germany, beautifully crafted, wood and brass, delicate coils of wire, a compass needle right at the center.
I can almost picture Schweiger in his workshop, hunched over that very instrument, carefully adjusting those coils and watching that needle move.
It must be incredible to see it in person, to hold a piece of history like that.
It really makes you appreciate a different era of science when researchers had to build everything themselves.
It does. This whole conversation has really got me thinking about how important it is to remember the people who came before us.
I agree. It's so easy to get caught up in the latest and greatest technology and forget about the long journey that got us here.
It's true. And scientific progress is about the journey as much as the destination.
Right. It's about all those individuals who dedicated their lives to pushing the boundaries of knowledge.
Their stories show us that science isn't just about facts and figures.
Yeah.
It's a human endeavor,
No.
driven by passion and curiosity and a desire to understand the world.
Well said. This deep dive has been incredible. We started with a simple question about the earliest electromagnetic instruments.
And we ended up going everywhere.
I know, right? We talked about discoveries and innovations and rivalries and even the philosophical debates about the nature of electricity itself.
It really shows how a seemingly small observation, like the twitch of a compass needle, can spark a scientific revolution that still impacts us today.
It does, and it reminds us that the spirit of scientific inquiry is timeless. As long as there are curious minds out there asking questions and exploring the unknown, there's no limit to what we can achieve.
I completely agree.
So to everyone listening, we encourage you to embrace that curiosity, keep asking questions, and never stop exploring.
You never know what amazing discoveries you might make.
That's right. Thanks for